Every hour the sun's energy falls on the planet is equal to the amount of energy used by the entire human population in 1 year. The energy from the sun is in limitless supply. Unlike oil or gas, solar power is a reliable source of energy whose prices never fluctuate. Solar energy is free. How does it work? Solar electricity is generated using photovoltaic cell technology that has been optimized over years of research. Simply put, the greater the intensity of the sun, the greater the current of electricity. Solar panels collect sunlight and turn it into direct current or DC electricity. Even on cloudy days, your panels will absorb sunlight. The system's inverter then turns this DC electricity into the same electric current that comes from your traditional utility lines. Your solar electric system is connected directly to your utility power supply so that the excess power from your solar panels will be fed back to your local utility company.
When solar panels produce the most electricity, no one is at home. And when people return to their homes, the sun is about to set. Demand and supply are not in sync, a basic problem for renewable energy. The network is supposed to transport power to where it's needed at the moment. But the existing power lines are overloaded. They can't take on any further green electricity. The expansion of renewables is endangered. Help could come from a combination of solar panels and lithium-ion batteries. These high-capacity batteries can store solar energy for longer periods of time, relieving the strain on the network. The problem is, batteries like these are expensive. One way to make solar power storage more economical is to increase the efficiency of the entire system containing the solar module and battery. That's why scientists and engineers at a Munich semiconductor company are working to make the flow of electricity between the solar cells and batteries as loss-free as possible.
We know that the price for lithium-ion batteries will come down over the years. Nevertheless, an important challenge will remain, which is to make sure that all the energy that is generated by the solar module is effectively stored in the battery, which means we need to have an energy transfer chain which doesn't lose any energy at all.
The problem is, lots of sunshine causes the solar cells to deliver lots of electricity at a high voltage. And when there's little sunshine, the cells deliver little power at a lower voltage. The batteries, however, need a constant voltage level for charging. That means the voltage of the solar modules has to be lowered or raised by several hundred volts without any loss of energy. To make that possible, semiconductor engineers manufacture special microchips in a complex process. The chips are only a few thousandths of a millimeter thick. Several hundred fit on this wafer. The ultra-thin chips work like a switch and are part of an electronic component. And this component is integrated into a special electronic unit that has the task of providing the battery with just the right voltage. And it manages the flow of electricity with as little power loss as possible. If there's lots of sunshine and the solar cells are delivering a lot of power at a high voltage, the switch closes only for a short time. The result? Electricity flows into the battery at a lower voltage than it comes out of the solar module. If, on the other hand, the solar panel delivers power at a lower voltage, The switch remains closed for a longer time period. This results in electricity flowing into the battery at a higher voltage. That means the silicon chip always adjusts the voltage to exactly what the battery needs. And since the chip is just a few thousandths of a millimeter thick, it offers practically no resistance to the power. As a result, energy flows through the chip with almost zero loss.
With the new thin wafer technology, we provide the solar industry with a new and much more efficient way to store solar energy.
Ultimately, the system of solar cells and energy storage becomes more economical. As part of a European pilot project, the use of this technology is being tested in several private households. For example, in this family home in Bavaria. Here, Fraunhofer scientists are testing a brand new system. For the first time, they're combining into a single unit the electronics that bring solar power to the correct voltage with the batteries that store the power. The entire unit is the size of a small cabinet that would fit in any garage or basement. The efficient electronics regulate the flow of electricity between solar cells, batteries, and the power network. When the sun shines, electricity flows into the home's power lines. Just enough to power the dishwasher, refrigerator, and washing machine currently in use. When the cells produce more electricity than currently needed, the excess solar power flows into the battery. If no one is home and the washing machine isn't running, the solar power also flows directly into energy storage. After sunset, the battery provides the house with electric power. In this way, solar power provides around 80% of a family home's annual electricity needs. During this experiment, the new technology remains under scientific observation. The goal is to make the combination of solar power and energy storage more economical with the help of efficient electronics. And if the new technology takes off, it will benefit more than just private homeowners. PV battery systems take the strain off power networks. They spur the growth of renewable energy because locally produced electricity is also used locally. If solar power is both produced and consumed within households, that reduces the amount of electricity that has to flow through the power lines. That leads to greater network capacity, making room for more renewable energy. And maybe when night falls in the future, we can just turn on the sun.
The sun. It is a unique, clean and infinite source of free power, delivering more than 1,000 kilowatt-hours per 1 square meter. 1,000 kilowatt-hours is the amount of energy found in 100 liters of heating oil. Wouldn't it be wonderful if we could use the energy from the sun? Solar energy, wind power and water energy are forms of very clean energy generation that can be converted to, for example, light. Photovoltaic systems use solar cells to convert solar energy into electrical energy. Solar cells are usually made of silicon, that is a semiconductor material, which means that it can conduct electricity under some conditions but not others. When looking at the periodic table, we see that silicon is part of group 14 and is situated between aluminum and phosphorus. That being the case, a silicon atom has 2 electrons in its first shell. It has 8 electrons in the second shell, but it has only 4 electrons in its outer shell. The outermost electrons are called valence electrons and are of utmost importance because all silicon atoms consist of not more than 4 valence electrons. However, all of the silicon atoms will form bonds by sharing electrons to achieve a full outer shell with 8 electrons, which makes them very stable. In order to disturb the stable state, doping atoms are purposely inserted into the silicon. When boron is combined with silicon, free holes will be created because boron has only 3 electrons in its outer level. With 5 valence electrons, phosphorus creates additional free electrons. And that's where the magic happens. A solar cell consists of 2 silicon panels sandwiched together. One layer is doped with N-type dopants, the other is doped with P-type dopants. To allow an electrical flow of electrons, a front and a back contact are installed to the layers. Glass is installed on top of it to protect the layers and the electrical contacts from damage. Now it's time to take a closer look at the area between both layers. In the N-doped semiconductor, there is an axis of electrons. In the P-doped semiconductor, we observe positively charged electron holes. The electrons in one layer will find their corresponding free holes in the other layer. Consequently, an internal electrical field builds up at this transition that does not permit electrons and holes to jump into the other layer. However, if photons hits the silicon layers, electron-hole pairs will be created. If this happens in the electrical field, electrons are moved to the N-doped layer and holes are moved to the P-doped layer. The system will fall into a state of imbalance because of an excess of electrons in the N-doped layer. The corresponding holes can be found in the P-doped layer. It goes without saying that these free electrons and free holes try to combine. However, the electrical field does not allow such a condition. But if you connect the top layer to the other layer, for example by using a cable, you will see that electrons are traveling to the free holes. This flow is called an electrical current and can, for example, light a lamp. Solar panels can be installed on the ground or on your roof. The solar cells collect the rays of the sun and convert solar radiation into direct current, which is eventually converted into more usable alternating current by a piece of equipment called an inverter. Connected to the inverter is another device that is going to measure the electricity produced by the photovoltaic system. Generated electricity may then be reimbursed by your electricity supplier.